Before you get too tired of me going all philosophical, let's have a look at a really cool quiz called Computers Are Fast. I'll put a link in the description. They give you simple loops and ask how often can a typical computer run this in a second. So for example, on the left here, a loop that just counts up a number. I'm going to guess we can do that, let's say, at somewhere near the clock speed of our processor, which is in the gigahertz range. I mean, we have to increment I, compare it to number, and then we add to S. Conditional control flow can be very expensive in a pipeline processor, but this is a loop and it can probably predict pretty well that we're staying in there most of the time. In this quiz, we're allowed to be off by an order of magnitude, so let's just say 1 billion. Okay, in their experiment it was 500 million. Fair enough. Question 2. Similar thing, but now it's Python. That's an interpreted language, and I've heard that loops specifically can be pretty slow in Python. And this is just a loop. Maybe there's memory management going on, I don't know. Let's be dramatic and call it a factor 100. Let's guess 10 million. Close enough for the quiz, but not actually that close. I maybe should have thought about this some more. Now, I'd like you to take the rest of the quiz and really think about it. If you just YOLO through it, you're not going to learn anything. Pause the video and come back when you're done. Welcome back. I hope you had fun. And don't worry if it was difficult. This is not something that we're used to thinking about, and maybe it'll help you get a bit of a feel for these things. One thing you'll have noticed is that caching is a big deal, the memory hierarchy. When I was first learning about systems architecture, my professor said the number one way to make a system faster is caching. He would say, if someone wakes you up in the middle of the night in a panic, oh no, the system is slow, we must make it faster now, lives depend on it. Your answer is caching and you can go back to sleep. The fastest way to compute something is not to. Well, that depends on how you're going to look it up, of course, and it can introduce variance in how long something takes, but a lot of the performance of modern computers depends on stacks and stacks of caches. It's caches all the way down. That makes things fast, usually, but it also brings with it certain performance pathologies, as you saw in the last 2 quiz questions, for example, and it's good to be aware of that. Here's a table from 2015 that's close enough for our purposes. It has the latency for various levels of the cache hierarchy, including RAM, conventional hard disks, and the internet. You see that main memory is at least a factor 500 faster than even solid-state hard drives. If you compare the access time for main memory and a conventional hard drive, well, I've heard that compared to picking up a pen from the desk in front of you, as opposed to flying all the way to New York and getting it there. There is a similarly amazing difference between the processor's own registers or a low-level cache versus main memory. If you're going at the speed of the CPU, main memory is amazingly slow. A lot of pipelining is in place to try and hide these latencies, but now you see that it is especially bad if you have to look something up in memory, and then depending on what you get, you do something different. Try not to do that if you can help it.